Hello everyone, I'm Joon-Seok Kim from George Mason University. On behalf of our team, I will give a presentation about vehicle relocation for ride-hailing. I believe most of you have an experience of using Uber or Lyft app as a user. However, have you ever thought about the drivers? What does Uber drivers app look like? Uber tried to make it easy for drivers to recognize where the surge, boost, and incentive and the area are located. Then users don't need to wait for a long time. However, Uber cannot drivers to move to particular places simply because it is totally up to drivers. Then what will happen? This is New York City. On the right bottom, you can see a flock of yellow taxicab waiting for the passengers in the JFK airport. We call this effect herding. So this herding occurs because they don't talk to each other and are very competitive. The focus of our research is on solving this problem. Let's assume that you are in Manhattan, New York City. You take out your ride-hailing app like Uber. Then you hail a car. The assignment authority will assign the nearest empty car to you. Then the driver picks you up and will drive up to your destination. In this process, the driver has no control. However, after drop-off, the driver should think, but where will be the better place to move? Here, each driver logic comes into play. We use New York City yellow taxicab data, which include the pickup and drop-off location and time. Our goal is to build a spatiotemporal resource model for the prediction such that it minimizes the average search time of drivers. We leverage an open source simulation called Competitive Searching Testbed concept. In this framework, we focus on developing a data model and intelligent agent logic to relocate agents when they are cruising. Let me introduce our solution. White dots are an empty car and red dots denote a waiting passenger. At 8 a.m., there are a lot of car demands on the Midtown area. While many agents are still moving to the center on the left, there are a few empty cars on the right. The left is using the random destination, which is baseline, and right one is our solution. After the rush hour, many cars become empty. It means oversupply. But there's not much thing we can improve for it. As you can see, our agents stick to the center area and random agents are moving far from their location. So they take the highway all the time because the agent moves through the shortest path. Agents cannot communicate each other, so they need to rely on resources distribution over time. Around 3 p.m., something interesting happened. You can see a temporary demand peak. It is important timing to reduce search time and wait time. The key idea is to predict spatial temporal distribution of resources and agents. After 5:30 p.m., agents are busy to come back to the center after drop-off. Surge pricing might help to meet such demand. We introduce our approach in two steps. First, vehicle relocation, which is based on probabilistic sampling approach. Second, we predict spatial temporal resources. Let us assume the driver located here in the center. Although many resources are distributed in the northern part and southern part, our agent won't go too far. Their decision is based on the resource distribution and distance between the current location and resources. Instead of taking all the resources into account, we sample them based on the resource distribution. Then we calculate probability mass function, taking this exponential function, that is distance to the gamma power. The denominator is just for normalization. We call this gamma distance decay factor, which determines the probability. This decay factor depends on the data, more specifically the number of agents and resource distribution. So how can we get this gamma? We can obtain the value in an empirical manner. Here the x-axis is distance factor. We have three measures: agent search time, resource wait time, and resource expiration percentage, which have different weights. Here we have to consider search time first. These two of the range is the best candidate, and comparing other measures, we chose a value minus 0.5 as a distance decay factor. It plots look like this graph. Also, we obtain sample size in an empirical manner. Here, x-axis is a sample size. When we choose 5 or 6 samples, we get satisfactory results. Let me come back to the local search approach. How can we guarantee that agents avoid herding without knowing where others are located? We can consider more options to spatially distribute drivers. What if drivers are spatially distributed from the beginning? So we come up with the idea that each driver has their home zone. This home zone doesn't necessarily mean their real home location, but the driver preferred that location or direction. And I often heard that from the taxi and Uber drivers. Let's assume that this red box is the yellow one's the home zone. For this driver, we give a more weight northern sample than the southern sample. So if the distance of the samples are similar, and they are more likely to select samples toward their home zone, and we hash drivers' unique ID to decide their home location. We analyzed spatial-temporal patterns. This is heat map that shows a month pattern. Rows are the spatial zone and columns are temporal slots. If we pick this one distinctive column, it is a daily pattern, and this shows a weekly pattern. The main idea is to find representative patterns that leads to predictions. The patterns are considered as a latent feature. Thus, to find the latent components, we employ the negative matrix factorization. It results in a two matrix W and H that represent the resource distribution. Through experiments, we found the 6 features that provide fair enough outcomes. Then what does it look like? The resource can be decomposed into the 6 latent features. As you can see the heat map here, each spatial feature presents a unique distribution. This feature captures interesting spatial patterns. For instance, one of the component shows spatial concentration on one region. This area turned out New York Penn Station, which has huge text demand. Then the spatial components are combined depending on the temporal patterns. So if weights are given for each feature, then we'll get the mixture of three features similar to this figure. Now I'm going to talk about the time horizon and temporal resolution. In our model, spatial temporal resource distribution is represented in a discrete manner. The size of a bin or slot affects our model. This is an example of resource distribution of one region in a day. It has 24 temporal slots, meaning each slot is 1 hour range. By increasing the number of slots, we can get more granular temporal range. This is about 30 minutes, and this is a 20-minute range. We are interested in how far agents need to predict. The time horizon denotes a time window that agents consider for their prediction. In order to define the best time horizon and temporal resolution, we conducted experiments, and the darker region denotes less search time. So we chose 150 minutes as a time horizon and 20 minutes as temporal resolution. With a test dataset, we obtained these results with respect to three evaluation metrics. X-axis is the number of agents. As the number of agents increases, the search time of our solution getting close to the random destination. Why? If you look at the right figure around 8 to 9,000, agent covered all the resources, so difference is not that significant. Also, we found that the performance of home zone is similar to that of the local search. If resource prediction is accurate, then the local search is better. On the other hand, if resource prediction is inaccurate, home zone approach is better. Our approach is an extension of our previous method that won the first place in ACM SIG Spatial Cup 2019. In conclusion, we tackled the novel problem of competitive spatial temporal searching for ride-hailing services, which aims at guiding drivers to areas that are likely to have a passenger searching for the ride. We approached the problem of the guiding drivers who cannot currently be assigned due to the lack of the available the passengers, and to maximize the chances of the finding a passenger in the near future. We employed a non-negative metrics factorization approach on historic data to predict future resources. Using these predicted resources, we used a probabilistic sampling approach to guide agents to predicted locations. We choose a probabilistic approach to prevent agents from greedily herding in the same area, while other areas become undersupplied. Our approach weights the sampled locations by distance to avoid extremely long trips while still allowing the flexibility to escape unviable regions. We provide thorough parameter calibration to obtain the best result for the example of the Manhattan. However, the different areas made requires different parameter settings, and experimentation for different area is required. Also, the car speed in this research is subject to speed limit of the road regardless of time and traffic condition. Thus, a traffic model is then needed to adjust our search heuristic to ensure that the need of the customers in slow traffic region can be met. If you have any question about the research, please contact us, and thank you for your attention.